Git software.
In software development, Git/Git/ is a distributed revision control and source code management system with an emphasis on speed. Git was initially designed and developed by Linus Torvalds for Linux kernel development in 2005. Every Git working directory is a full-fledged repository with complete history and full version tracking capabilities, not dependent on network access or a central server. Git is free software distributed under the terms of the GNU General Public License version 2.
History.
Git development began after many developers of the Linux kernel chose to give up access to BitKeeper, a proprietary SCM system that had previously been used to maintain the project. The copyright holder of BitKeeper, Larry McVoy, had withdrawn free use of the product after he claimed that Andrew Tridgell had reverse-engineered the BitKeeper protocols. Torvalds wanted a distributed system that he could use like BitKeeper, but none of the available free systems met his needs, particularly in terms of performance. Torvalds took an example of an SCM system requiring 30 seconds to apply a patch and update all associated metadata, and noted that this would not scale to the needs of Linux kernel development, where syncing with fellow maintainers could require 250 such actions at a time. His goal was for patches to take 3 seconds. Torvalds had several other design criteria. Take concurrent version system, CVS, as an example of what not to do. If in doubt, make the exact opposite decision. Support a distributed, BitKeeper-like workflow. Very strong safeguards against corruption, either accidental or malicious. These 3 criteria eliminated every then existing version control system, except for monotone. Considering performance as well excluded this too. So, immediately after the 2.6.12 C2 Linux kernel development release, he set out to write his own. Torvalds has quipped about the name Git, which is British English slang roughly equivalent to unpleasant person. Torvalds said, "I'm an egotistical bastard, and I name all my projects after myself. First Linux, now Git." The man page describes Git as the stupid content tracker. The development of Git began on April 3, 2005. The project was announced on April 6, and became self-hosting as of April 7. The first merge of multiple branches was done on April 18. Torvalds achieved his performance goals. On April 29, the nascent Git was benchmarked recording patches to the Linux kernel tree at the rate of 6.7 per second. On June 16, the kernel 2.6.12 release was managed by Git. Torvalds turned over maintenance on July 26, 2005 to Junio Hamano, a major contributor to the project. Hamano was responsible for the 1.0 release on December 21, 2005, and remains the project's maintainer.
Design.
Git's design was inspired by BitKeeper and Monotone. Git was originally designed as a low-level version control system engine on top of which others could write front ends, such as Cogito or StGit. The core Git project has since become a complete version control system that is usable directly. While strongly influenced by BitKeeper, Torvalds deliberately attempted to avoid conventional approaches, leading to a unique design.
Characteristics.
Git's design is a synthesis of Torvalds' experience with Linux and maintaining a large distributed development project, along with his intimate knowledge of file system performance gained from the same project and the urgent need to produce a working system in short order. These influences led to the following implementation choices. Another property of Git is that it snapshots directory trees of files. The earliest systems for tracking versions of source code, SCCS and RCS, worked on individual files and emphasized the space savings to be gained from interleaved deltas, SCCS, or delta encoding, RCS, the, mostly similar, versions. Later revision control systems maintained this notion of a file having an identity across multiple revisions of a project. However, Torvalds rejected this concept. Consequently, Git does not explicitly record file revision relationships at any level below the source code tree. implicit revision relationships have some significant consequences. It is slightly more expensive to examine the change history of a single file than the whole project. To obtain a history of changes affecting a given file, Git must walk the global history and then determine whether each change modified that file. This method of examining history does, however, let Git produce with equal efficiency a single history showing the changes to an arbitrary set of files. For example, a subdirectory of the source tree plus an associated global header file is a very common case. Renames are handled implicitly rather than explicitly. A common complaint with CVS is that it uses the name of a file to identify its revision history, so moving or renaming a file is not possible without either interrupting its history, or renaming the history and thereby making the history inaccurate. Most post-CVS revision control systems solve this by giving a file a unique long-lived name, a sort of inode number, that survives renaming. Git does not record such an identifier, and this is claimed as an advantage. Source code files are sometimes split or merged as well as simply renamed, and recording this as a simple rename would freeze an inaccurate description of what happened in the immutable history. Git addresses the issue by detecting renames while browsing the history of snapshots rather than recording it when making the snapshot. Briefly, given a file in revision n, a file of the same name in revision n. 1 is its default ancestor. However, when there is no like-named file in revision n. 1, Git searches for a file that existed only in revision n. 1 and is very similar to the new file. However, it does require more CPU-intensive work every time history is reviewed, and a number of options to adjust the heuristics. This mechanism does not always work. Sometimes a file that is renamed with changes in the same commit is read as a deletion of the old file and the creation of a new file. Developers can work around this limitation by committing the rename and changes separately. Git implements several merging strategies. A non-default can be selected at merge time. Resolve, the traditional three-way merge algorithm, recursive, this is the default when pulling or merging one branch, and is a variant of the three-way merge algorithm. When there are more than one common ancestors that can be used for three-way merge, it creates a merge tree of the common ancestors and uses that as the reference tree for the three-way merge. This has been reported to result in fewer merge conflicts without causing mismerges by tests done on actual merge commits taken from Linux 2.6 kernel development history. Additionally, this can detect and handle merges involving renames. Linus Torvalds, Octopus, this is the default when merging more than two heads.
Data structures.
Git's primitives are not inherently a source code management (SCM) system. Torvalds explains. From this initial design approach, Git has developed the full set of features expected of a traditional SCM, with features mostly being created as needed, then refined and extended over time. Git has two data structures, a mutable index, also called stage or cache, that caches information about the working directory and the next revision to be committed, and an immutable, append-only object database. The object database contains four types of objects. A blob, binary large object, is the content of a file. Blobs have no file name, timestamps, or other metadata. A tree object is the equivalent of a directory. It contains a list of file names, each with some type bits and the name of a blob or tree object that is that file, symbolic link, or directory's contents. This object describes a snapshot of the source tree. A commit object links tree objects together into a history. It contains the name of a tree object, of the top-level source directory, a timestamp, a log message, and the names of 0 or more parent commit objects. A tag object is a container that contains reference to another object and can hold additional metadata related to another object. Most commonly, it is used to store a digital signature of a commit object corresponding to a particular release of the data being tracked by Git. The index serves as connection point between the object database and the working tree. Each object is identified by a SHA-1 hash of its contents. Git computes the hash, and uses this value for the object's name. The object is put into a directory matching the first two characters of its hash. The rest of the hash is used as the file name for that object. Git stores each revision of a file as a unique blob. The relationships between the blobs can be found through examining the tree and commit objects. Newly added objects are stored in their entirety using zlib compression. This can consume a large amount of disk space quickly, so objects can be combined into packs, which use delta compression to save space, storing blobs as their changes relative to other blobs. Git servers typically listen on TCP port 9418.
Implementations.
Git is primarily developed on Linux, although it also supports most major operating systems including BSD, Solaris, OS X, and Microsoft Windows. The JGIT implementation of Git is a pure Java software library, designed to be embedded in any Java application. JGIT is used in the Gerrit code review tool and in a Git client for the Eclipse IDE. The Dulwich implementation of Git is a pure Python software component for Python 2. The libgit2 implementation of Git is an ANSIC software library with no other dependencies, which can be built on multiple platforms including Microsoft Windows, Linux, Mac OS X, and BSD. It has bindings for many programming languages, including Ruby, Python and Haskell. JS-Git is a JavaScript implementation of a subset of Git.
Git server.
As Git is a distributed version control system, it can be used as server out of the box. Dedicated Git server software helps, amongst other features, to add access control, display the contents of a Git repository via web, and help managing multiple repositories.
Remote file store and shell access.
A Git repository can be cloned to a shared file system, and accessed by other persons. It can also be accessed via remote shell just by having the Git software installed and allowing a user to log in.
Git daemon install.
Git daemon allows users to share their own repository to colleagues quickly. Git interweb allows users to provide web view to the repository. As of 2014-04, interweb does not work on Windows. Both can be seen in the line of Mercurial's HGServe.
Git-lite.
Git-lite is an access control layer on top of Git, providing fine access control to Git repositories. It relies on other software to remotely view the repositories on the server.
Gerrit.
Gerrit provides 2 out of 3 functionalities, access control, and managing repositories. It uses JGit. To view repositories it is combined for example with Gitiles or Gitblit.
Gitblit.
Gitblit can provide all 3 functions, but is in larger installations used as repository browser installed with Gerrit for access control and management of repositories.
Gitiles.
Gitiles is a simple repository browser, usually used together with Gerrit.
Commercial solutions.
Commercial solutions are also available to be installed on premises, amongst them GitHub software, using native Git, available as a VM, Stash, using JGit, Team Foundation Server, using libgit2.
Adoption.
The Eclipse Foundation reported in its annual community survey that as of May 2013, more than 36% of professional software developers use Git as their primary source control system, compared with 27.6% in 2012 and 12.8% in 2011. Open Source Directory OLO reports a similar uptake among open source projects. The UK IT jobs website itjobswatch.co.uk reports that as of late April 2014, 17.26% of UK permanent software development job openings list Git as a requirement, ahead of 16.35% for Subversion, 10.69% for Microsoft Team Foundation Server, 1.44% for Mercurial, and 1.13% for Visual Source Safe.